Okay, I'm back. I did a lot of sitting thinking yesterday about how I could make this good and like fix all the problems that I was encountering yesterday. And I think that I'm gonna stop working on the arch simulation for the moment, and I'm gonna start working on system Verilog. I'm not great at system Verilog. It's hacky been a little while, and I need to like get comfortable again and like get to using it. And like I feel like there are a lot of constraints in how it was working that are basically from me thinking about system Verilog as if it were C or C++, and like not being able to have access to like clock cycles and be able to do that type of like thinking through the problem, I think is a big part of what is producing some of the problems with my design. So I did thinking yesterday, and I think I'm going to change the architectural design a little bit. Should be able to go to the zone first. This will be, yeah, okay, and then if we go into arch, and then so the big problem that I was having was on commit, right? In commit, we had this rob entry, and there's like a lot of stuff in this rob entry, but on commit we were trying to write, oops. Oh, that was, how did I even press all of those keys all at the same time? That was impressive. Oh, still here, okay, yeah. Inside of the arf, right, I was trying to write to the arf the values, and I had to get them out of the PRT, right? And getting them out of the PRT would require one cycle, right? Per commit, which would, inside the pipeline, set me a stage back, right? Which is not at all what I want, right? Oh, that is not a good keybind to be using. I should change that. Settings. Hotkeys. Scene. Let's make that Control Alt 1. Okay. Oh. Now we go over here. Doesn't actually destroy my code anymore. Alright, I did want to be here, so I think we're on number 11 is the page note number. 4, 5, 6, 7, 5. I'm missing some of them. That's a good question. I don't know, but then never mind. These are the notes I was working on. Oh, they gotta be somewhere. They're just staying here. Put them up here. I did. Right. And you can see 9, 8, 9. Maybe I never started it. It would be the sheet if it existed. So we're on 10. Okay. So, problem was that we would hit an exception inside of the rob, right? Which means I need to flush out the rob or do all these other things, right? As it goes. It's problematic. Fundamentally, this is problematic. So what we want to do instead is have this not be a problem. Amazing. wow, so cogent, so understandable. So right now, what we have is we have the arf, right? And that's being written to from the rob is going to the PRT, and the PRT is writing to the arf the value, right? And then on exception, right, the arf is then overwriting the PRT, right, with the original values, and then the rat just gets reset, right? Fundamentally, though, what's happening is we're making the PRT values align with the rat values at the position of exception, right? The arf is tracking the state at every commit, right? And then on exception, we're updating the PRT and rat to match what is happening in the arf, right? So the arf tracks state at commit, right? And then on exception, we are making rat and PRT match state at commit, right? But what if we keep a copy of the rat, I'm calling this the C rat, the commit rat, that just tracks the state the rat should be if the rat were tracking commit state instead of speculative state, right? So the problem that we're running into is that, let's say we have like some instruction that's like add x1, x2, x1, and then we have an interrupt, right? And then we have add x1, x2, x1, right? This is gonna be like add like P20, P5, P10, right? Interrupt, add P10, P5, P6, right? These numbers aren't going to line up after the interrupt, right? And this will be the rat state before the interrupt reaches the top of the rob, right? Which means that we need to track what the rat should be at point of commit, right? What's really nice, though, about this is that in the code, we look into the rob, right? Like I have so many fields in here because I just like wasn't really sure what I needed in here. But we already have this physical destination, right? Which is what we need to be tracking, and we already are tracking the destination. So we won't have to touch the data structure in regards to these very much because we already are storing all of this information, right? The only thing I haven't figured out yet, right, is how do we I should put this on questions. Questions is on page 5, right? Page 5, yeah. How do we reset rat to OG register source? Yeah. We do. So now the question becomes, how do we update PRT to match commit state, right? how do we clear all of the entries that are speculative beyond the ones that are in the wrap, right? Do we just have to loop through all of the entries? Like, that's going to take time, that's going to take execution cycles, right? Like, is this actually it'll probably be slower. This is definitely smaller, right? But is this even a good idea, right? Like, how do we update the PRT to match the commit state, right? Like, it'll be pretty easy just to have another 32 entry table that's tracking all those registers. But how are we going to make the PRT track like all the things that have been speculatively allocated after the last committed instruction, right? How are we going to know what those registers are? I guess we could I don't know. We could have, right now, the PRT is just like a flag array, where if there's a free entry, it finds it and then it overwrites it, right? So how are we going to go through and find all of those entries, right? We could change the data structure to be a type that inherently tracks, you see with my finger what I'm thinking, we inherently track the order that the things are requested for allocation, right? Like, we could use a circular buffer, right? But then how do we find what the head should be? How do we update the head to be where the largest head for any of those physically allocated registers? We know all of the PRTs that we are going to be using, right? Because they are, we know all the PRTs that we're going to be using because they're in the committed wrap, right? The problem is that we don't know what do we not know? We don't know what the biggest one is going to be. And also, circular buffers necessarily operate from, like, 2 is sometimes bigger than 31 if 2 is in the allowed range, right? So we need like a distance, and then it starts spiraling into complexity very quickly in that state as well, right? So like, how are we gonna come up with a, like, I don't know what to do. Let's see, did I write any thoughts about this down somewhere? We know what all the physical. No, that would be so slow. Right? How do we do this? Because we need to update the PRT to not be storing. Our speculatively allocated registers. We could add another bit to the PRT. That tracks. No, we just have to iterate through the entire thing. Like, even if we stored another bit, what would that even be doing? You know, like, it would track. We know that all the instructions previous, like all the instructions previous to committed instructions will be free. That's why we're storing the previous physical destination, right? Because we're going into the PRT and we're telling it, hey, this is marked as free, like you can use this now, right? Every time we commit, we are effectively updating. The previous reference gets freed out of the PRT, right? Previous reference gets freed out of the PRT. It's so expensive to write to so many entries in an array at once. Like we could use like liveness, right? Where only the entries that are in the committed rat update the PRT, right? And then we check for liveness inside of like we use liveness and free together, right? And then normally all instructions are live, and then they all get set to 0 except for the ones in the PRT, which get set to 1. Except for the ones in the committed rat, which then get set to being live. I need to prove, and I don't know how to make proofs about hardware, but this would be a good time to learn. I need to prove that if I track okay, let's say that the PRT is a circular buffer. I think that's what I'm leaning towards, right? Let's say the PRT is a circular buffer, right? And we're going to have some tail, and we're going to have some head, right? When we are adding new instructions that get allocated at the head, right? Right? And the freeing happens this way. I want to track another value here, which is going to be the commit pointer, right? And so that at point of commit, I can just reset head to being commit, and then we know we're good, right? I need to prove at exception no instructions, no periods past commit are live, no instructions before commit are dead. My handwriting is so bad for that. Okay, I need to reread that. No preg from commit to head are live. No preg. Tail to commit are dead. Right? That's what I need to prove. I don't know how to prove this. So we're just gonna mess around, you know. We're gonna see if we can come up with something. So let's go to 11. See, prove circular PRT physical register table. Okay. I need to figure out a way to like represent these ideas. I am hitting like speaking decision paralysis because I don't know where to go because we've hit the limits of my knowledge pretty like clearly. This is not like it feels true, but I don't know that it's true and I don't know how to prove that it's true. Right? So maybe we're gonna just hit up the internet, you know, open up good old Firefox. Okay. All right. So I think let's start with just writing down assumptions and then see if we can build out of there. My internet is being really slow. I think it's because I'm running on an $100 laptop and it's barely being able to handle rendering frames out of OBS. So let's see, we know that, okay, wait. What even is? What is anything? What is the commit head, right? Where do we get that from instead of our code? For the rob, we don't have a commit head. The commit head is just the head of the queue. Let's say the commit head is the so let's just make it the preg of last instruction committed. assuming current is exception. Okay. My handwriting is really not good today. I think I need to drink more water. I'm quite distracted today. It's not good. I was turning the music off. Okay. Right. So preg of the last instruction committed, assuming that the current is an exception, right? What would make this true? First of all, we need to know what our tail is, right? Because no other instructions are going to be, no other instructions are going to be executed from Rob, right? No other instructions are going to be executed from Rob. Yes. So if no other instructions are going to be executed from the Rob, okay, so we have 0 to 31 as our architectural registers, right? We need to prove that from tail to commit is equal to these 0 to 31 architectural registers. Or okay, we need to show that for all R that belongs to PRT I such that tail is less than I, which is less than or equal to commit. Let's put a circle around that to mean circularly. Fucking, I don't know, dude, right? Okay, so for all these registers that belong to PRT, with I, right? No, it's not a good way of doing this. Okay, wait. R. No. 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 Okay. Let's say, like, it is true. True that for all that in registers tail to commit, NP registers from tail to commit, all architectural registers occur can occur multiple times. Should they be allowed to occur multiple times? The answer should be no, right? Like, they shouldn't be allowed to occur multiple times. Once, and all others are free. It is true that in vreg from tail to commit, all registers occur once and all others are considered as free. Okay. This would work, right? Because this would be our proper state. On commit, we know that must they also be present? Must they also be present? They must also be present. I don't know. Let's mark that down as a subproblem. Subproblem number 9. I feel like it's number 3. Let's just make it subproblem number 1. Number 1, must all areg be present. Of course they would. They have to, because no other instructions are gonna guess. All other areas be present. Yes. No other instructions will be executed. Yeah, okay. So how is tail defined? Tail is Ooh, this is also assuming tail is at and is it? I don't know. I don't know. Let's think about this. So we know that on commit, previous preg for destination is marked free. Previous preg for destination. The committing happens in order, necessarily, right? That's the whole point of the committing. We also know the commits happen in order. We know the commits happen in order. Okay, and we know that, we don't know this, but I should add this, we know all instructions, all preg from mispredicted branch must be marked free. Right. But will those be after the commit head? Because commit head will be up to the branch, and then when the branch is mispredicted, that's when that is being committed. So all of our pregs allocated in order. Yeah. Or rather, we should say a preg is allocated in order up to exception, right? Which will happen either on a branch or like a load or a store or something, right? The only thing that it wouldn't occur is on a branch, right? It wouldn't be in order. And then we would hit an exception on the branch prediction, right? But up to that branch instruction, because we're only working on the one ahead, we know that the pregs are allocated in order, yes, in order of instructions. Right. this must also be working from the assumption that we have allocated all of the registers in the existing code, because p-registers are only allocated on declaration, right? So let's say we only use 2 registers in our code, then only 2 will exist in only 2 will exist in our thingy. Wow. Ooh, struggling with words out here. Only 2 will exist. In our rat, that's not true though, because the rat will have all the entries. So what is the default value for our rat, right? Do we, by default, pre-allocate all of our instructions to 0 in the preg file? Or do we do something sneaky, like we assign them all to like preg 0 and then we make the circular buffer skip 0? Like, do we just like OR it with 1 always? So that would work. But the circular head reset. Well, the circular cube should be a power of 2, so that way we don't have to do conditions. Okay. What's the default for a rat, bro? I say we default allocate. Like, power up 0 to 31 on PRT and assign to rat. Right? Is that correct? Because we don't want to be using all that space, right? Because what if our code like never uses register 12, you know? And then we could have more physical registers in our other parts of code, right? Like we could be doing other stuff. Yeah, I think that's how I'm gonna do it. Default allocate those, so we know that they're all gonna exist. But that all, but we don't have the architectural register file anymore, right? Because that's the whole point of this, is to get rid of that. So we're no longer wasting a cycle. Okay, so I know this is a terrible idea. So maybe I'm just gonna ignore it, actually. I can't, why am I like this, dude? Problem that I'm hitting, right, is like, if we're allocating in the PRT, let's say to like x1, right? Pre-allocate to x1, right? And then we don't use x1 ever. We never use x1 in our code. It's still gonna take a slot. Right? So we could like have x1 and then like a bunch of like used and then freed and then used and then freed and then used and then freed instructions, and then like x3, x2, x5, blah 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 blah, right? And then we have the commit head. This is a whole lot of wasted space, right? Like we could wrap all the way around back again, and there's just going to be these like blobs of sitting registers that are never used, right? For long stretches of time. So how do we get around that, right? Like I think a circular queue probably is the best idea, because it gives us this behavior that we want. Okay, this isn't gonna work. At all. Which means we're gonna have to do something more complicated. It's gonna take up more space, right? However, this problem would exist even if I went back to the ARF design, right? Because of having our circular PRT. Right? Okay. Let's do PRT design. So we want, what do we want? What do we want? What do we want? We want no jams. Right? Must have table. Right, we know this. PRT is a table. We can't have jams. We know that we're doing a mapping of it being present and if it's free and its value, right? And then it has the ID. And that's our table. What I did in code is iterate through all entries and find free. Right. So in code, what I could do is iterate through all entries and not in committed rat mark free. That's how I was doing the allocation of the code. I would not work in hardware, right? So what I need to do instead is, what I was going to do is use a circular queue through the table, right? However, this gets stuck. this circular queue replaces this iteration, right? Fundamentally, we need some way of doing iteration through all these entries without actually doing that, right? This idea of the commit head and rolling back to the commit head, I think, is really clean. So how are we going to make that real? I want a circular queue, right? Like, I think that is the answer to this problem. I think that this would be provable. I don't know how to, but I'll figure that out, because I can figure anything out, because everything is easy, actually, if you haven't learned that already. So what are we doing? We need a circular queue, right? But it can't get stuck, which means that we can't track the instructions themselves. We have to track a reference to them. Would that work? I think that people do this. They use something called a free list, right? Where they keep track of the free physical registers instead of having the freeness be a flag. We're gonna leave it as a flag for now because well, it really sucks to write to everything in a loop. So do we even need this? I don't know. We're gonna leave that for later. So let's say that we're using a free circular queue. Right. So we're using a free circular queue. Then our PRT is going to be the ID, present flag, and the value, right? The circular queue, the free list, is going to be of the ID, the preg, right? So the free list is going to start free list starts as free is length number areg plus negative areg plus number preg, right? Starts as the number areg to number preg. Yeah. Okay. So when we allocate something off of the free list, we're going to eat the first entry beyond 0 to 31, let's say, and then we execute that instruction. It will mark, which will move the tail upwards, right? Then we're going to allocate a new entry on the free list when we do the free, which will be for the last physical destination, right? So we're gonna add the last PRT to the head, right? And that'll be at commit. At commit. Okay. So we're gonna have our free lists. This is gonna be a set of free lists, right? So this is gonna be the tail. It's gonna be the head. Right. I need another colored pen, I fear. And this should be in a circle. So this is our tail. And our head, right? Then we're gonna have our tail and our head. On allocation. On allocation, our tail is going to advance, and our head is going to stay in place. I should have made that clearer. Oh well, it's not erasable. 0. Okay. We also are going to need C head to be here. And as the tail is advancing, nothing has been committed yet, so C head is still going to be here. Right? So on alloc, I know I already wrote it, but I can't help myself. Let's assume that there are several more allocations that occur. So like we have tail, and then we have head, yeah, so we're removing entries by eating them out of the tail, and we're adding entries. So on commit, we free previous location, which adds to the queue for the circular queue. Which means that our commit head moves forward. Right? Yes. This writes the old value into the queue, right? So this empty space in the free list represents allocated preg greater than the number of architectural registers. Do we just move the tail to the head? Right, would that work? Can we just move the tail to the head? Right? Because we know that they're going to be committed in order, right? And we know that, like, let's say instruction 0, that writes to like x1, gets committed, right? x1 will be what we add, or preg1 is what we get added to the circular queue, right? However, nowhere in the circular queue will we have the allocated form of, oh, we might though. We might. We'll never have the allocated form of, what's it called? We'll never have the allocated form of the preg for that instruction, right? Because we know that we're doing the allocations in order, and we're doing the deallocations in order. Doing the allocations in order, and we're doing the deallocations in order. We're doing the allocations in order, and we're doing the deallocations in order. If every instruction uses, we're not committing the register, but we could have the sources of later instructions, but those will get reset by the committed rat, right? Because the committed rat will be using only these committed values. I think this should work. I just do not know how to prove it. Okay, I think this design could certainly work. So 13. Is that right? Yeah. We want the PRT prove PRT with circular queue free. So how do we do that? We need to show that okay, so we're assuming last instruction committed, current instruction an exception. Okay. we need to show that for all of the pregs that belong to the commit rat, there does not exist a preg that belongs to the free list. Alright, that's what I need to prove. For all of the registers, for all the pregs of the circular rat, does not exist no, that's just wrong. For all version 0, preg does not belong to free Q. Okay. So how does an instruction get added to free Q? So we start with rat is equal to rat, which is equal to ret at I is equal to I. Free Q is equal to free Q at I is equal to I plus number of a reg. Yeah. Free Q head is equal to 0, free Q tail is equal to 0. Okay, so this is our base state. What can we do from this point? So let's say we have an instruction. An instruction can get added to the queue. What can an instruction do? An instruction can have a destination. An instruction can commit, and an instruction can, what's it called? cause an exception. So we need to show that at an exception, for all instructions before let's call this P1, property 1. P1 holds. P1 held / holds. So at exception for all instructions before P1 for it, comma, P1 held / holds. Okay. So what does this mean? That means that all instructions before must have committed. Right? They must have committed. Committed. All instructions before must have committed, which means that all instructions before must have committed. Right, so we need to show must have committed. Okay, so for our base case, which is I1 goes to an exception, or I0 goes to an exception, by definition, so then let's do base case I1, which goes to exception, we know that I0 must have allocated and committed without exception. Means allocation I0 must have allocated and committed without exception. Which means that the I0 dot preg belongs to FreeQ and belongs we can just use a comma, FreeQ comma rat on allocation. Right, because we take out of the FreeQ and we put it into the rat. Right? On commit, see rat, oh my god. On commit, FreeQ is overridden for I0 dot last preg. Rat updated for I0 dot preg. Right, which means that I0 dot preg belongs to crat comma rat, but does not belong to FreeQ. Okay. So then we just have to show that this is weird. I don't think that this proof is correct. I'll have to have a friend look at it. Like I know that this proof is easy. Like I'm just proving a circular queue, basically. But it feels like I'm missing something. But like I know I'm not. But have I over-assumed too much? Like I'm thinking about the processor, I'm trying to come up with like different ways that this could all be interacting and I just can't come up with something. So it's probably right, you know, maybe it's right. Wouldn't that be cool, right? The real question is, how, in this inductive hypothesis, do I say that we assume that instruction, we know that this is true if instruction k minus 1 has an exception. We know this is true if k minus 1 has an exception. How would we then prove it for instruction k being the one that has the exception? We say we know that instructions up to k minus 1 have executed successfully. Yeah, we assume that instructions up to I k minus 1 have executed successfully. And then we have two cases for instruction k. If instruction k commits successfully, then we know that this is true. If instruction k is an exception, then we know that k minus 1 is true. Yeah. Is that a proof though? I don't know. Yeah, okay. Yeah. Let's assume up to I k minus 1 has executed successfully. Okay. Case 1. Okay, is exception. Current instruction commits. Period. For all is exception. Two. Okay, commits. P1 holds. When both free Q allocation and commit occur in order. Okay. Bang. Bang. I believe that I just proved that. I mean, I should probably prove this if I was being anal, but this was fun. Okay. So we know this needs to be a circular Q with our PRT, and we just need to have those allocations. Nope, we're so lost. Come on, let's actually think here. This is our PRT design. This is done. It's what we're working on before this. Getting rid of the ARF, which we did. Questions. Show. Do we solve the 1 cycle stall of updating from FU signal? Where do we store the values of physical registers? We did this. Yeah. It's in the PRT. Cool. So now, I think we could just write the PRT, and we could write the free Q. And we could write the rat and the commit rat, and then that would be a chunk of this done. We would need to design for width, right? Like if we want to have instruction windows, we're going to need to have our allocation occur we're going to need to have like multi-channel read and multi-channel write, which I don't really know how to do or make good, etc. But we shouldn't have to touch, like on reset, on free. I think this should carry me all the way through. The rest of it, like, I think this design is solid. We're obviously gonna have to make the Rob interface with it. We're obviously gonna have to like keep doing things. Also, like if I want to introduce branch tags, so like if we are speculatively executing a branch and then we reach another branch and start speculatively executing that branch. Wait, some of those instructions how's that? They're going to be dependent on okay, so branches happen like every 5 instructions, right? which means that we should be able to know what instructions belong to a branch. Yes, Dylan. Yes, that is good. We should know that. But why does this matter? If we are currently committing instructions at our present state, right, and we have speculatively executed a branch later on that is not yet being committed, right? If we know that that branch on its execution does not, like if that branch we've misspeculated its execution, then we can free the rob, all entries in the rob that match said branch. We can mark them as invalid. Okay, right now what I'm thinking about is, I don't know if this is like even a reasonable thing to be thinking about, but let's say that we're executing code, right? Yeah, we're executing code and we hit a branch, right? And this branch sends us down to this branch, which sends us here, right? If the instructions in this branch, right, are not dependent on the instructions after this branch are not dependent on, let's call this window 1, I know we're going to call it what it is, which is a basic block 1, basic block 2, basic block 3, and basic block 4. Let's say the 4 instructions in basic block 4 that are not dependent on instructions from BB2 or BB3, right? We could still be executing these. Like, these could still exist in our ROB, and these could still commit if these could still be computed because all their things are ready, right? So if we were able to track what branches last updated a register, right? We're able to track what branches last updated a register. If we're able to track what branches last updated a register. If we're able to track what branches last updated a register, then we wouldn't have to throw away the work that we did theoretically on these instructions that would be ready, right? Even though we speculatively executed these, and maybe we're supposed to go over here, and then over here. Oh, but what if it got updated in the other branch? We have no way of knowing that information. Right? If it didn't get touched here, but it did get touched in any of these other paths, it couldn't be committed until these instructions are committed, which would require these instructions being inserted before these instructions, which is not viable, right? So why would I keep track of this information? Because I remember last time I attempted this problem, I did this. But I don't remember why I kept track of this information, right? Why did I keep track of what the branch was doing? I'm just looking at my old code right now. Probably not super interesting, but if we're flushing everything, I don't want to flush everything on a branch misprediction, right? I don't wanna. Like, couldn't we execute like both paths of the branch in parallel? and then whichever one is taken, we keep the information from. Like if we have a for loop, right? And it's like iterating. I guess we'd be doing too much work, but it would keep the IPC high. But I guess we couldn't use a circular queue for the ROB, right? Because it would be in a branch that's not real. Well, the ROB could skip over that, right? Problem is tracking. Is there a way that we could make this work? Right? Hmm. 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 Oh, oh, wait, what if I'm like huge? Okay. This would be nice. We don't want to throw away work, right? And we will know whether or not branches were speculated correctly before they're executed, probably. Right? Where we're having this like buffer of instructions that are executing, right? And one of our highest priority items is getting these branches executed early, right? So the reservation stations / issue queue should pick these branches to execute, right? And we could honestly add scheduling logic. Maybe we should add a note, right? Add scheduling logic to prioritize branch preds for execution. Right, because this is where work gets thrown away primarily, right? So we know that when branches are executed, right, they're doing one of two things, right? They're either being executed or they're getting like the next. If we remove all branch instructions but treat the path that the branches take, path of execute instructions, instructions as one continuous list, fully unrolled, right? We would be able to never have a branch misprediction, right? Like if we wrote a program that has no branches, just raw computation all the way through, right, there'd be no misprediction. So what we want to do is we want to simulate this, right? Because we know that at commit every instruction is going to be at commit every instruction is going to be in order, right? Even with these branches, right? If they're speculated correctly. Right? If they're not speculated correctly, then we cannot know for sure if these instructions have been speculated correctly. However, since we know that the branches and their children will be in order to commit / exception and in order to in order for what's it called, and in order for ingesting and fetch, decode, right, ingesting into rename, we can use this property that we proved of the preg, that after any current instruction has been committed, that we know that the previous ones were also good, right? Yes. No. Drat. Okay, so what we could do, what I'm thinking here, and this is probably what I was trying to do in my last time, and this is actually definitely the reason why I failed, is because I didn't get this working, and that's because I didn't have my PRT as I wasn't able to recover properly on branch misprediction, and I had to add like 3 cycles for recovering for branch misprediction because I tried to implement this branch masking thing. Anyways. So what I'm thinking is we could have our circular queues, right? Where we have our head, then we have our tail, right? And this head is munching. This is the commit head, right? And this tail is tracking whatever has been issued, right? And this space in between are the current in-flight registers. not registers, physical registers, right? All we have to do is add more trackers, right, that correspond to branch 1, right, correspond to branch 2, right? We only have to track these things theoretically, right? So then if we've, let's say, mispredicted branch 2, all we have to do is roll back our tail to branch 2 and not all the way back to head, right? Because we also need to roll head back. No, but head is the committed state. Because these are all the free ones. So we're unallocating these registers by doing this. We'd also need to update our rat, right? So we'd have our rat and we'd have our C rat, but we'd also have a B rat. Right, so we need to make a copy of our rat for every branch, which will then overwrite the rat entries. Wish there was a cleaner way that I could do this, right? Because like I don't want to like be writing rat from like 6 different places, right? And also these take up not that much space. These don't take up that much space. The problem is the writing speed, right? The problem is the writing speed. This is going to take almost no space. This is going to take almost no space. The problem is the connecting of all these things into each other, right? The committed rat we shouldn't have to touch at all, right? The committed rat tracks itself beautifully. Problem is writing these branched rats to the rat, right? How many cycles? We could write, of course, we could make this be a 2-cycle write back where we write C rat and B rat to some temp rat, right? And then temp rat writes to rat in the occasion of an exception, right? Which would then reduce the loading. No, because then we have to do the same thing with all these going into T rat, which is then writing to rat. It's just offsetting it by a cycle. Because T-Rat could be wired to all of these with a mux, but that's what would be happening anyways, right? We would have like if rat overwrite is true, begin, then rat at I is going to be set to something. Could these all be wires? No, they don't have to be regs, but we could rerun them. We could have these all dumping their data into the rat. And it just comes out of a mux, right? You just like select out of an index, right? And so then it would be like, we just call it, we could call it trat, or wrat for wire rat, and wire rat at selector, right? And then we just connect all of these wires together into trat combinatorially. There has got to be a better way to do this, but I can't think of it. I wish I could like just like store the differences between crat and brat, right? And then write crat and then write the changes. Alright, because I know these changes are not going to be very many. The problem is doing them all at once. Right? And also like I think that would take at least 3 cycles to do. And this would be pretty fast. This could be 1 cycle. This might take a lot of space though, because we need to add extra writing ports to the rat. But how many times are we writing to the rat? We write to the rat either from the crat, which is 1, or on allocation, which is 2. We never need to read to it from brat, so we could have, we would just have to add a writing port every single time. I don't know how terrible of an idea this is. What else would we have to deal with? We would only need to take, like, we just need to copy these values every time we encounter a branch. And so all instructions follow a branch. We would have to take it at the beginning of the branch. See, now I could just ignore this, and I could get it working, and then I could add this later to make it faster, which I honestly might do. This is seems doable, and like it would cause a lot of speed up theoretically. Especially if you keep predicting correctly. But also, how many of these things do you even need, right? 2 of them. 3 of them would be nice, because especially if we're muxing with the crat, right? 3 of them would be nice. So 2 to the n minus 1. Because then we could just encode it as the value, right? So like does it have 4 values? 3 branches. There's 1. Honestly, we could just have 1. Which just rolls back the branch prediction before it occurs. If we can just have 1 extra bit everywhere. The only I think I should shelve this. But I think I could get this to work. I think I should stop touching this. What did I work on previously? The PRT. This PRT circle, this, I should prove this if I want to. But I know it would work. Just by get, but that's not a particularly good trust for anything, right? I don't know. Let me be back in a minute. Text. Let's call it text. What's the text going to be? Derby. Okay. Okay. And he's back. Crazy. Ooh, droidcam.app. You can see what I'm using for the desk. Nice. So, what am I doing? What am I doing? We got the PRT. I should just implement the PRT design. And then once that's done, then I can implement the rename stage fully, because I have a half working decode, I think. So I'm actually just going to get rid of this to do from yesterday, because we're no longer working on the arch thing. What was I supposed to do here? I did that. I didn't do that. I didn't do that. Okay. We should do those two and stuff. Whatever. Whatever. So let's start writing some code about that, huh? At least, I know, right? Right. So, I'm not going to worry about this. I'm actually going to... Yeah, okay, so let's go ahead and go to branch, and then check out local branch trunk. And then if I go branch, local branch, cool. So I shouldn't have anything inside of branch, local branch, object files, Okay. Okay. Sweet. So let's go into SRC. We're not in decode. This is, what is this stage called? This is called rename, right? Sure hope so. Sure hope so, but yeah. Okay, so I'm gonna call the folder rename. And then what's this gonna be called? Is it gonna be called the physical register table? Yeah. PRT dot system verilog. Yeah, I would love to create a directory. Blah 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 blah. Fly checker. Okay. Module. PRT. Thing. Wrong one. And module. If X begin and honestly, oh, and it, okay. Well, verilator mode, I might just not be in the mood for anymore. So how do we write this nicely? And let's write up a description of what this is. This is the physical register table. It is responsible for holding the values that are used in computation. It is not the registers that are defined in the ISA or it's the architectural registers. Rather, okay, cool. So the PRT table has ID goes present by free followed. I don't, we just don't need free anymore, just value. Yep. Superb. Security table and the value. Dun, 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 dun. I don't know how to write system verilog. Like, I don't know what the good, professional, well-designed way of doing this is. Like, should I make a struct and then it implements the struct? Right, should it be called a PRT entry? Should I have a reg resident reg like, is this how you make good system verilog? I don't know. Oh, is table a type in system Verilog? A, B, C, D, do, do. Interesting. Why are you red, brother? Didn't even anything over here? The Zoinga? No. I'm confused. That's okay. PRT table, let's just call it PRT. No, that is what it is. Why are you, why is table a keyword, dude? We're asking the good old-fashioned internet out here. Dinosaur. Oh, let's just call it the let's just call it the PRT. Nobody cares. I don't care. No one cares. And it's gonna be of size PRT size -1, 0. Okay, and then enter PRT size is equal to 64. You can do damn truth tables? What? Ridiculous. It's a primitive. What's the difference between a primitive and a module? When do you use them? Questions. Notes. What is a primitive? What? I'm just so largely confused. What is a primitive when of a module? Okay. Okay, we have our peer T. What does this need to do? Okay, the PRT needs to be assigned present or not by listening for what do you call it in English, dude? Alert. Dashboard. Needs to be assigned to present or not by listening for alert. Entry can be assigned present or by listening for alert. Value is assigned true. Value is assigned by alert. Zero. Okay. The ROB doesn't tell the PRT what to do. The PRT is just going to listen for the same input wake-up signal as everyone else, right? Okay. What does it need to output to? The PRT needs to output to the free queue. Needs to output to rename stage logic handler. Needs to output to the function name is queue. Okay, value free queue rename stage. Could we track this presentness elsewhere? No, but it's an optimization, right? We track presentness. No. Values used in issue queue for determining if what is it called, micro up is ready a name up, view up. Is ready. Value. Source when .vreg is written value is set. Used in functional units for computation. Signed language is completed. Okay. Signed on 6. P value is set. Comes through the alert signal. Do. Okay. Does it need to output to the free queue? Not even a little bit. They're independent, but they need to track the same state. Free queue tracks the state of this module. We could have the free queue. Possibly we could make the free queue internal to this module. Right. Possibly. Okay, so we need one. No, we don't, right? This actually needs to go to the free queue. Free queue. Oh. We only need this output to. No, you do need to do this. Okay. That needs to send the value. Needs to send the present bit. Okay. We could, of course, separate this structure up so it's not all combined together. In so doing, we would allow for more optimal present checking because it's only a single bit, right? Like, because it's going to be a pretty big array. Probably should be several sizes larger than this. Either 128 or 256. Note, we could decouple the present bit into its own array data structure so that it's smaller and such. So the functional units don't need to read the present bit, right? Only the rename stage needs to read the present bit. The functional units need to read the value out, right? Maybe. I need to close that window. So if we do separate them, yeah, we're gonna separate them, okay. Make this a wedge, PRT present. And then to define value with as 32. Okay, and then let's move this to some header / interface. Okay, and then we're gonna have a reg packed size value width. This one there. I'm just gonna call it PRT value. I'm just gonna go from PRT size -1 to 0. Okay. Awesome. Awesome. Sweet. So we need to have okay, so for each of the PRT, for each functional unit connected, we need 2 read ports to the PRT value. PRT Does she ever get overwritten? Yes, she does sometimes. How does she get overwritten? She gets overwritten. By the output signals. Her allocation is handled externally. Okay. For the width of rename stage, we need 2 read ports to the PRT present value. Each. How do we do that, dude? Okay, yeah, so without these parameters, parameter, PRT, rename, read, PRT, present ports. Let's look at 4 wide. And parameter PRT value read ports. I think that's just 1 for the moment. And then we're gonna have parameter PRT right. No. PRT table right ports. Wide. There should be 8 actually, because each one is going to need a read port. Do not have any idea how to do this. So how do we make? Oh, I'm getting a call.